Lesson 12.2, Net Force and Free Body Diagrams. Free body diagrams are used to help visualize net force calculations. When drawing a free body diagram, you first need to determine all the forces acting on an object, as well as their direction and relative size in comparison to each other. The free body diagram will show all of the forces acting on the object, and you draw the forces as arrows coming out of the object. And you will include the direction of the force by drawing the arrows in the correct direction, and draw them the correct size in comparison to each other. The relative magnitude of each force should be in your diagram as well. For example, we'll draw a free body diagram for pushing a box along the floor. We start by drawing a box. In fact, most of our objects that we draw when drawing free body diagrams will be boxes. It's easy to draw a box. The first force you should always put on, as long as it's an object on Earth, is force of gravity. And if it's not falling, this is balanced to some degree by the normal force. The applied force is the pushing force. And as long as the problem doesn't say otherwise, you should also assume in this unit that there's friction opposing the applied force. Here's another example. A skier sliding down a hill. Now, in the case of a hill, we've got a little bit of a downward falling force due to gravity. Normal force isn't quite enough to hold back gravity. We draw the skier as a box because boxes are easy to draw, and the first thing we do is draw the force of gravity directly down. The normal force is perpendicular to the slope, so it comes out at right angles to the slope. And the force of friction opposes the motion, so it goes opposite to the direction we know that the skier will go. There isn't actually an applied force pulling it down the hill. There's a component of gravity that causes the down the hill velocity. F net, the net force, is the vector sum of all forces acting on an object. It's the total unbalanced force. It's whatever's left after everything else is balanced out. To calculate F net, we must use our vector addition techniques. These are our collinear vector addition, as well as perpendicular and vectors at angles. To combine all forces acting on the object. First example. Two men are attempting to push a car along a flat road. One man pushes with a force of 120 newtons. And the other pushes with a force of 200 newtons. And both of these forces are to the east. Remember, force is a vector, so direction matters. The force of friction is 150 newtons, and I'm not going to give the direction because that's for you to determine. We start by drawing a free body diagram. We'll draw the car as a box and draw in our two applied forces of 120 newtons and 200 newtons to the east. Now we know friction will oppose the motion of the car, and it will oppose these two applied forces. So we draw it in the opposite direction, 150 newtons to the west. This is collinear vector addition. There's no perpendicular vectors and there's no vectors at angles. For that reason, we can just use addition and subtraction normally, making sure that west direction is subtracted. 120 plus 200 minus 150 for the west gives us 170 newtons to the east. For our second example, we'll look at some vectors at angles to each other. A crate is pulled with 3 cables. The tension in the first cable is 400 newtons. At an angle of 20 degrees north of east. The second cable has a tension of 350 newtons at an angle of 30 degrees south of east. The third cable pulls at 200 newtons directly to the east. The force of friction is negligible. You're going to see the word negligible a lot in problems. When I say friction is negligible, what I mean is that it's so small that it doesn't actually factor in, or it's not important. So it just means ignore friction. We'll start this problem with a free body diagram. The crate is drawn with its 3 forces in generally the right direction. 200 newtons, 350 newtons at 30 degrees, and 400 newtons at 20 degrees. There is more than one or more than 2 forces acting on this crate, and they're all at angles to each other. In this situation, when you have more than 2 forces to add at angles, the best way you can solve it is to use an XY table to keep your components organized. An XY table will allow you to keep track of which ones are X's and which ones are Y's and do your calculations accordingly. To do this, you draw a table where one column represents X and the other column represents Y. In the Y column, you put all Y components. In the X column, you put all X components. And then at the bottom, you find the total of all the X's, the total X, and the total of all the Y's, which is the total Y's. Here's how we do it for this problem. Our 400 Newton vector has 2 components, the X component and the Y component, at an angle of 20 degrees. The 350 Newton vector has an X component and a Y component at an angle of 30 degrees south of east. We have a third vector as well. This is our 200 Newton vector, and since it's directly east, it's only an X component. Our XY table contains all the X components and all the Y components. This is 200 newtons, which is our east component, 400 cos 20, and 350 cos 30. Since these are all eastward, we don't have to worry about any subtractions. We can just combine the 3. In the y direction, we have 400 sine 20 and 350 sine 30. But be careful. The 350 is in a southward angle, which means that we need to make sure that it's negative. The total x comes from combining our 3 eastward x components. It's 878.98594 to the east. The total y is 38.19194 to the south. Once you have the total x and the total y, you still have to put them back together using perpendicular vector addition techniques. The magnitude of f net is found by x squared plus y squared square rooted. To calculate this, we put our total x and our total y in, 878.9 and its decimal places squared plus 38.191942 squared gives us a magnitude of f net of 880 newtons. The angle, because all forces are vectors and they require angles, is tan negative 1 y over x. Putting in our numbers, this is tan negative 1 38.191942. This is to the south, divided by 878.98594. This is to the east. This gives us an angle of 2 degrees south of east.